All right, welcome back. Now, at the beginning of this unit, I told you that these sinusoidal functions, sine and cosine, they were going to be really useful in modeling repetitive scenarios, contexts that had some sort of repeating situation. And so today we're going to be looking at those. And the first one I've got for you isn't really that much of a context. It should be pretty familiar. We're going to talk about a large wheel with radius 2 feet rotated at a constant rate. And we're going to track the movement of point P at the start position in the figure. So this is very much like the unit circle, very much like what we're used to. So at time t equals 5 seconds, the wheel has completed one full rotation and P is in the same position it was at t equals 0. All right, so that means that the period of f is going to be 5 seconds, right? If it went all the way around and came back one to where it started and it took 5 seconds, that's one revolution in 5 seconds. Okay, and I really want to emphasize that because in these contexts, they're not going to just be like, oh, the period of the function is this, unless they give you an equation, and even then we kind of have to decode using the formula period equals 2 pi over b. So we're thinking of a number, like how long does it take to get back to where I started, number of seconds per revolutions. Okay, well, they told us 5 seconds is one revolution. We'll see later, it might not always be one revolution that they tell us about. Okay, that's going to be 5 revolutions divided by... No, 5 seconds divided by one revolution. I'm saying it backwards, okay? But we'll talk about frequency in the next video. Okay, so I'm going to say the period is equal to 5 seconds. There's going to be far more interesting questions about this situation than just what's the period. What are the maximum and minimum values of f? Well, okay, remember the f is a sinusoidal function used to model the y-coordinate of point P. All right, so if we think about, the point P starting there, then after a while it went up here, that's going to be the maximum value of P. Maximum value of F. The maximum y-coordinate of P is going to be, I might just say F equals 2. And then the minimum is going to be f equals -2, the minimum y-coordinate, and that would happen down here at the very bottom of the circle. What is the amplitude of f? Well, the amplitude is half the distance between the maximum and the minimum. We don't have a graph for this thing yet, but we could say that we've got the maximum and the minimum, the distance is 4, so the amplitude is 2. Okay, I guess we can go back to the figure if we need it eventually. All right, so now we need to write an equation for f of t. All right, so this thing is starting in the middle, kind of in its medium value, halfway between the extremes. So it's starting at its midline and increasing. So if I was going to draw a picture of that, I think that's what I'm going to do for these type of problems. I'm going to recommend that we draw a box. I'm going to make a sketch. So we started in the middle and we were increasing. So that's regular sine. That looked like it was a little more than halfway. Okay. So that's going to be the shape of my graph. Okay, and then this was 0. It went up to 2 and down to -2. And we started at t equals 0. We said the period was 5 seconds. Okay, so that's going to be 2.5, 1 1/4. That would make this 375. Okay, I'm not sure if that's going to be necessary. No, it's definitely not. But I've got a kind of a graph, and it'll be easiest for us to write an equation, in my opinion, from a graph. All right, so I'm thinking that f of t is going to equal some number of sine of something. And then plus 0 is the midline, so I'm not going to add anything on the outside. There will be 2 sine, because the amplitude is 2. And on the inside, we're going to need to figure out what's the value of b. Well, if the period is equal to 5, and period equals 2 pi over b, that's going to tell me that b times, 5b equals 2 pi. Yep. And that's telling me that b is 2 pi divided by 5. Okay, and there's not going to be a phase shift because we're starting at t equals 0. We started at the midline while we were increasing. This is like an ideal scenario. So 2 pi over 5 multiplied by t minus 0. I'll just say that's my equation for f right there. All right, so let's do another context. A cat is breathing at a constant rate. When the cat has fully inhaled, his lungs hold 1.2 liters of air. When the cat has fully exhaled, there are still 0.4 liters of air in his lungs. Completes one breath every 2 seconds. Okay, so again, seconds per revolution. That's going to give me the period, so the period is going to be 2 seconds. Period equals 2. Now, I know that I'm going to need to use that. Maybe I'll actually switch the color to be a little more consistent with how I've been doing, like in the lessons and the other lessons and the homework videos and stuff. If I've got the period, that's going to be related to the value of b, and I know eventually I'm going to have to write an equation for v of t, so I'm going to need that value, so I might as well do that right now. Remember, period equals 2 pi over b. That means b is going to need to equal pi. Okay, now the midline of v. Okay, now the midline is going to be halfway between the maximum and the minimum. So I would average the two to find that that distance, or no, not that distance. The distance is the amplitude. Pardon me. The midline is just going to be the average of 1.2 and 0.4. So 1.2 plus 0.4 all divided by 2. That's going to be 0.8. Okay, and that'll be the midline. Okay, the amplitude, that's where we're saying, okay, how far do I go from the midline to the maximum or from the minimum to the midline? That's going to be 0.4. And at time t equals 0, the cat is fully inhaled. Sketch one cycle of the graph of v. Okay, and I'm noticing I didn't draw the x and y axis, or the whatever in t axes on the last one, and that's because I really I was only using the graph to find an equation. This one, if they're asking me to make a graph, maybe I'll put in the axes, maybe I won't. We'll see. All right, so starting at t equals 0, the cat is fully inhaled, so it's got its maximum amount of oxygen, which I think I'll come back in and do in a second. So halfway in between, it'll be at its minimum, and then at the end of the period, it'll be back where it started. So I'm just going to kind of go halfway in between these points, draw the best version of a sinusoidal graph that I can, and that'll definitely be good enough. Okay, this looks like the graph of positive cosine, right? Because it's starting at the maximum. I can label the midline with 0.8. Okay, if the amplitude was 0.4, I'm going up to 1.2 and down to 0.4, which makes a lot of sense because they told me the maximum was 1.2 and the minimum was 0.4. Okay, the period started at 0. We determined the period was had length 2 seconds, so 1, 0.5, and 1.5. And so if we had to draw in, like a y-axis and maybe, let's see, it would probably be an x-axis, or, oh man, okay, well, that ended up being all right. That could be an x-axis there. Okay, I guess really it should be a v-axis and a t-axis. Okay, and then there we go. Now we've got ourselves a nice graph. All right, and then an equation for v of t. I'm going to definitely want to start with cosine. V of t equals some number of cosines of, okay, leave plenty of room, plus something else. Okay, so kind of, the amplitude is going to be the number that goes on the outside, so that's 0.4. Okay, cosine of b is pi. Okay, the phase shift was 0 because I started right there at t equals 0. So pi times t minus 0. And then the number I add on the outside will be the midline. And that's going to be 0.8. All right. And so there, that's all for the cat's breathing. In example 3, kind of already spilled over in that area. In a certain town on another planet, the daily number of minutes of sunlight follows a sinusoidal pattern. The function L of t, so in this one, they're going to give us an equation. And actually, before I go too deep, I'm going to just kind of take a step back and look back at the ones that we've done. Notice how the first one we got some art and then just a description. The art wasn't really all that helpful. It kind of helped us decide what to start thinking about. Okay? Second one didn't even come with any art. Okay, it just was just a paragraph. Okay, and that can happen too. This next one is going to come with an equation given. We're going to have to extract all the same information out of it. It'll just be kind of backwards. Another thing that they can do, and we'll see this later on in these notes, they can give you a table of values for a sinusoidal function. And so that'll happen too, and so we'll see all those situations in in these notes, also in the homework and practice, because we need to be ready for any of these. All right, so on this one with the daily number of minutes of sunlight thing, we're going to say we first want to sketch the graph. Well, we're going to need to do all the old stuff. So start with the midline. It'll be the 730, the number that's added on the outside. The amplitude will be the 202. Okay, the phase shift is looking like 0 because I'm not seeing t added or subtracted to anything. Okay, and then the period, that's going to take a little bit of work. Okay, so I'll get that from there. Period equals 2 pi over b, where b is pi over 100. So I'm going to take 2 pi, and I'm going to multiply it by 100 and divide it by pi. So that's going to equal 200. So the period is 200 days. Okay, and then if I'm going to sketch the graph, I'm going to start with a window. Okay, this is a negative sign. Okay, so it's going to start in the middle and it's going to go down. Best I can map this out before drawing segments. Ooh, that was really, I don't think that was curved enough. It's showing definitely that curvature. Okay, so that's a negative sine graph. Okay, the phase shift was 0, so I started at 0. The period was 200, so that'll mean each kind of square would be 50. And then the midline was 730. And that would make plus 202 would be 932 minutes up there. Subtracting 200 would be 530. And so if I subtracted 2 more, that would be 528. And that's a really good graph. That's a graph of one cycle. I can draw the y-axis here, and maybe the l-axis. I guess it said y equals L of t. And then that'll be the t-axis right there. Okay, how many days make a year on this planet? I would think, assuming kind of like similar terminology to what we use here, that the period would be 1 year. If you think about the number of minutes of daylight, it increases and then it decreases. It hits maximum and it hits minimum. And I think we'll get into that, down below, not to get too much into like the geography or the anthropology here, but I thought it would make a good example. Okay, so how many days make a year? That's the period, 200 days. Because that's the period. Find the maximum and minimum number of minutes of sunlight in the city. When do they occur? Okay, well, the maximum is happening the number of daylight minutes at time t equals 150 days is equal to 932 minutes. Okay, and the minimum value is happening at 50 days. Okay, so L of 50 is equal to 528. And so those are the maximum and minimum and when they occur. And I might actually emphasize the when happening here and there, and the maximum values, those are the output values, the number of minutes. Okay, so which of these describes the day that the scientists started paying attention? And that's what I was talking about, the interpretation here. I'm going to have to think about this. Okay, so it's in the middle. It's not an extreme. And the solstices, these are the extremes, right? They happen in the summer and the winter, and the winter solstice is like the shortest day of the year, and the summer solstice is the longest day of the year. Big celebrations of summer solstice when I lived in Seattle. I didn't really understand it, but that's neither here nor there. It was a really long day though. Like the sun, it didn't go down to I feel like almost 10 p.m. In the summer there at the high latitudes. But what I'm going to say is that the solstices are out because I was in the middle. Okay, that's what I'm going to say, and I don't want highlighter. I just want a red pen. There we go. Get those out. Spring and fall. Okay, so this is going to be where the days are getting shorter, right? Because I'm decreasing. So the days are getting shorter in the fall. So I'm going to go with the fall equinox there. All right, now example 4, grandfather clock sitting on level ground. This is one where we're going to give you a graph. We're going to have to, interpret from the graph. The center of the face of the clock sits 5 feet above the ground. Okay, that makes a lot of sense based on the graph. Looks like y equals 5 is the midline. The graph of y of t, the height of the minute hand of the clock at time t minutes after 3 p.m., is shown in the figure above. Okay, so that makes sense. At 3 p.m., the minute hand would be up at the top of the clock, and so it would be at its highest point. Okay, the height of the minute hand. So we're going to draw a diagram to represent the scenario first. So I'm going to kind of zoom in here because this is going to... I don't want you to feel like you have to be able to draw too good of a diagram. What I'm going to do is I'm going to just say, all right, so the center of the clock is right... Well, actually, maybe I'll start over. I'm going to start with the clock. That's going to be a circle. All right, and then the center of the clock is 5 feet off the ground. So I'm going to just draw a straight line down. I'm going to say that's the ground level. And then this distance here is going to be 5 feet. Okay, the minute hand, maybe I'll draw that right here. That's the minute hand on the clock. That's the one that goes all the way to the edge. That's at a height given by y of t. Let's say, right, just like that. And that's going to be y of t. Okay, so we see that, it could be up at the top, and that would be a maximum of 6, and at a bottom of, at minimum of 4, right? Yeah, the radius is 1 foot. Okay, okay, that's the first question. What's the radius of the clock? That's going to be 1 foot. Okay, because the radius corresponds to the amplitude in this case, and I'm going up by 1 and down by 1. I usually use red for that. I can make that happen. Let's change that there, 1 foot. All right. Then use the graph to write an equation for y of t. All right, so we're going to have to figure out the period also. So I know, maybe I'll just start with what I know. So the equation for y of t, okay, it's starting at the top, so I want to use a cosine function. Okay, and the amplitude is 1, so it's just going to be 1 cosine of some number of t's, no phase shift because it's starting up at the top, plus the midline, which was 5. Just need to figure out what the period is. Now the period would be, this distance here from the top to the top. But I wasn't given that. I was given the top to a second bottom. So that's going to be 1.5 periods. So 1.5 times the period is going to equal the distance from the starting value 0 to 80. Really 80 minus 0, but well, I think that's 80. All right, so 1.5p equals 80. So 3 halves of p equals 80. And so p is going to equal 80 times 2 is 160 divided by 3, but 1 plus 6 is 7, which is not divisible by 3, so that's as good as I'm going to be able to write the period, 160 over 3. Okay, so I need period equals 2 pi over b. 160 equals, no, it was 160 over 3, is 2 pi over b, multiply here, 160b equals 6 pi. And all right, I might divide the 160 by 6, but that's like dividing... Wait, did I do that right? Yeah. Oh no, so, okay, it's just the same numbers coming back. Okay, so b, I'm going to just write it first, is 6 pi divided by 160. I'm going to divide both of those in half, and I'll get 3 pi over 80. Okay. So that'll be 3 pi over 80t, and that means that the period being 160 over 3 minutes, that's probably not meaning it's keeping accurate time. No, really that should be 90 minutes. That's what I would say. Right, 1.5 periods of the minute hand would be going all the way around once, and half of another one, that's an hour and a half. That's what I'm saying. No... period is not equal to 60 minutes. All right, now the last equation, or the last context I've got for you involves a table, and, on Saturday, cars started arriving at the grocery store at 4 a.m. Function R of t models the rate at which cars arrive in cars per hour for time t between 0 and 20 hours after 4 a.m. And then in calculus, you'd get the other function that tells you the rate at which cars were leaving, and then you can do all sorts of other stuff with them, especially if you had a calculator. The table below gives the values of R of t at selected values of t. Okay, so this is just the rate at which they are entering the parking lot. So they gave us the fact that we're starting with sine. So what I'm going to do with this, I would recommend just going from the table to a sketch of a window pane graph. That's going to be my recommendation for AP Precalculus. We just really stick to what we know, which is going to be the window pane method. And so, all right. But without, don't just say, oh, I've got to have a sine graph. Go with what they're telling me. T equals 0, we're starting at 10. So it goes 10, 120, 230, 120, 10. Okay, so it looks like 10 is the minimum and 230 is the maximum. Right, we're just going to, oh yeah, plus 120. So we know that we know that 120 is the midline. And actually that horizontal line is just in the perfect spot. And so 10 is the minimum and the maximum is 230. Okay, so I'm going from 10. Now I'm going to cut this interval in half, 0, 5, 10, 15, 20. Okay, so it looks like the maximum was happening at 10 hours, and then back down to the minimum at 20. I'm just going to cut it in half both ways. Draw the best I can. Okay. And now I'm seeing, okay, this looks like the graph of negative cosine. And so I'll show you we can work with that in the second part. But if they tell us I've got to be working off of the graph, or off of the kind of the standard sine function, then I'm going to have to adjust my approach here. And I don't think and maybe we did that a little bit in the last lesson, but I just want to reemphasize how we're going to do it. We didn't do it maybe in the last lesson, but we might have done it in the homework, right? So if we're thinking about positive sine, which I just want to think about positive sine. I'll deal with the amplitude and the phase shift and all that stuff later. Do you want to think about, or I guess I'm starting with phase shift. The graph of y equals positive sine x starts coming up through the midline. So it's going to be right here. So that's where I want to start. That's where I want to start my sine function. Okay, so that's going to be my phase shift. That was at t equals 5. Okay, when it was at 120 and increasing. And you could probably do this without sketching a graph, but you'd be visualizing the graph in your mind based on the table, which is really the same thing. So I might as well show you that visualization, even if you're not going to write it down on your paper. Okay, so at t equals 5, that's where the sine graph could be starting. Right, we could just add on a little bit more to the graph and just say, okay, well that would be one full period if we just added on. Let's see if that would work. Probably not, but I'll just get rid of that because that's just more of the graph, right? We just extended it a little bit. So finding the values of A, B, and C, all right, so A is going to be the amplitude going from 120 to 230 is an increase of 110. Okay, B, we're going to have to consider the period. The period is 20, so period equals 2 pi divided by B. Multiply that, divide by 20. So I'm going to say B equals pi over 10. Okay, C is the phase shift, so C will equal 5 because of the position of the graph where it's coming up through the midline. And then D is the midline, and that's going to be 120. And if we wanted to write an equivalent equation for r using cosine, we would say, all right, well, that would be r of t equals a would be the same, 110 cosine. But I'm thinking I might just like to call that a negative cosine since it started at the bottom. So negative 110 cosine of, again, pi over 10t. Okay, no phase shift because I'm starting at the bottom, like a negative cosine does, and plus 120. But I'd say there are definitely other right answers. That's something like r of t equals positive 110 times the cosine of pi over 10 times t minus, and we'll figure out a value there, plus 120. If we wanted to start with a positive cosine, we need to phase shift to a maximum. And so that would be right there at t equals 10, where I've got that maximum output value. And that would be t minus 10 there, and that would give you the same thing. Okay, so that's all the examples here. That's really all we're doing in this lesson, is we're just applying the techniques we learned in the last lesson to context, to actual real-world situations. So at this point, you need to just go in and practice on the homework problems and then other practice problems. And so that'll be all for this video. Thanks for watching.